We will attempt to solve this differential equation. This is one of our problems that we saw in our assignment, and this differential equation is not very difficult, but the way we want it formatted, we're going to want to solve for v, and solving for v explicitly could get a little tough, and it actually introduces some weird functions that we don't normally see, so we'll take a look at that. So this is our differential equation, and what we want to note is that v is our variable, or is our function that we're trying to solve for, and our independent variable t only exists in this derivative, and so this is an autonomous differential equation. So let's begin to solve for it. And the first thing we're going to do is we're going to combine this so that it's under one fraction, one term m. And so we're going to find common denominators. And then this way we can separate it. So if we take a look at this where we have m's, we can see that we can write it into one fraction. And then we'll multiply and divide both sides by whatever it is we need to multiply and divide by. And we note our v, and so we have this separated. We have our v and then we have our t, and so this is separated. Now we can take the derivative, or the antiderivative. Before we do that, I think there's a couple of cleaning up that we might be able to do and might be able to benefit from. Let's first rewrite our our equation. I'm just going to switch a couple of terms here. And then what I'm going to do is I'm going to group the first two terms in the denominator, just so I can kind of recognize something out of this. And part of the deal is to get rid of this k as well. And so if we think about dividing both the numerator and denominator by k, we can get this a little bit simplified. Now, most integrals with the variable in the denominator, some rational functions, especially when it's squared, it's good to get the other term in there squared as well. And so what we're going to do is we're going to, well, first let's combine the denominator for that extra term that we have, and then we'll talk about rewriting it in a way that might be helpful for us. So if we combine this into one fraction, now we can take a look at this fraction and say that we want that to be a squared of something. And so we can essentially write it as this thing, the square root of this thing squared. So this is how we're going to get ourselves all prepped up. Okay. Now the thing that's being squared is, of course, pretty complicated, but it's really all just a bunch of constants. In fact, m over k is a constant, and so this whole big thing is a constant. So because that's a constant, it's not going to affect any derivative or integrals that we're going to do. So why don't we just call that a constant, and then we can deal with it a little bit better. So the other thing I want to do is I want to bring this m over k onto the other side, and so we would divide by m over k, which is going to give us a k over m. So this is going to be our term that we're going to integrate. Now the left hand side looks like it's a difference of two squares, and we can factor that, and it looks like it's going to one way to approach this is to do partial fractions. By the way, you can also try to do this using trig substitution with v equal to sine theta. I think it would work out the same way. So let's split that up, and then the usual way to solve for partial fractions is to rewrite this as a sum of two different fractions with simplified denominators, and then solve for some unknown constants. In this case, it's a and b. So if we do some of that solving, we can use some, they call it the Heaviside Method or something like that. If we let the variable equal to alpha or minus alpha, then we can get b or a or whatever constants we're looking for. And so in general, your a is going to be 1 over 2 alpha and your b is going to be 1 over 2 alpha. So had alpha been equal to 1, then your a and b are just equal to 1/2, and then you can double check that to make sure that that actually works out. So now that we know that, we would be ready to integrate the left-hand side over here, which is the sum of smaller fractions, and these fractions have linear terms in the bottom, so we can just do a simple u substitution to get our ln's, and then so we have negative a ln of alpha minus v, and then b plus b times ln of alpha plus v. Now we know what a is equal to, and we know what b is equal to, so we can just replace those values with the 1 over 2 alpha, and then just for convenience, maybe we might want to combine it into the ln function. So we actually took it from this pre-integrated portion, and we did the work to integrate the left-hand side. And the integral of the right-hand side is fairly simple. K over m is a constant. So when we're going to integrate that, we're just going to get k over m times t. And then here is our result. Now, if we're fine with this as an implicit function of v, then we can be done. But we want to solve for v, and so solving for v is going to be a little bit of a challenge, but let's see if we can get that worked out. So how are we going to solve for v here? Let's take our equation and transform it a little bit. And we'll start by using a log rule by taking this 1 over 2 alpha down as a coefficient. And so we will have that coefficient there. And then let's bring that to the other side. Now when we bring that to the other side, we have to distribute the 1 over 2 alpha. Actually, brought to the other side, it'll be times 2 alpha. So 2 alpha k over mt, and then we have 2 alpha times constant c. So this c is not going to be the original c constant we got from integrating. And so just to denote that slight difference, I'm going to call it c1. c1 is actually c times 2 alpha. But since they're all constants, I'm not going to care too much about that, and I'm just going to call it c2. So now what? Now we have this. Let's try to transform that by taking the exponential of both sides, or you can think about it as the relationship between logs and exponents. So that would make the right hand side as a power of e, and then that would leave us with the left hand side of what's inside of the ln. So now we have this equation, and we're solving for v. Now it looks pretty difficult, but we've actually done things like this in second semester algebra class. And so what we're going to do is we're going to multiply both sides by the denominator, so that's alpha minus v. So when we do that, we're going to distribute the E power to both sides, or not to both sides, but we're going to distribute this so that we'll have an equal sign over here, and we'll have alpha times E to this big mess minus V times E to that big mess. And so here is our right-hand side kind of expanded out a little bit. So now we have this equation, and we're essentially going to combine like terms. So let me rewrite that equation again down here. So this is our equation. And then we're going to combine like terms. So on the left hand side, I'll keep my V's. So I have one V on this side. I want to bring this V onto the other side, so that would be V plus this V times E to the big mess over there. And then on the right hand side, I would have this alpha times this E to the big mess minus alpha. And so here's my two sides, and I'm solving for V, so I can just factor a V out of there. And that would give me a V times this thing, and then I can likewise factor out an alpha from the right hand side, and then I'll have this minus 1. And then now to solve for V, I simply divide both sides by that 1 plus E to that big term over here. And then now I have this big mess. V is equal to alpha times these two things. Now there's a 2 here that we have, and we'll take a peek at the definition of the hyperbolic function, and I'll show you why I did this move where I factored out a 2. So what I did was I want a 2 times a big mess over here. So what I'm going to do is I'm going to factor out a 2, and then I'm going to take a 2 out of C1, so I'm going to get another constant C2. C2 is actually C1 divided by 2, and so that's why I changed the C1 to C2 here. And then I also took my A and then kept that separate, and so now I'm kind of focused on this fraction. So the reason why I'm focused on this fraction is because of the definition of the hyperbolic tangent. So if you Google it or look it up in any of your calculus books, we'll see that the tangent hyperbolic is sinh over cosh, and the sine hyperbolic is e to the z minus e to the negative z divided by 2, and then the cosine hyperbolic is e to the z plus e to the negative z divided by 2. So the 2's would cancel. This is what you would have. Now you can also think about multiplying both sides by e to the z, or not both sides, but the top and bottom by e to the z. And so you get e to the 2z minus 1, e to the 2z plus 1. And that happens to be exactly this format, which is why I took that step to take factor out a 2. So now, if I look at this carefully, this expression 2 times that expression, this expression is going to be my z in my tan hyperbolic function. And so what I want to do is I just want to collect that, and then I have my alpha that is going to remain alpha, and so I have my solution to my differential equation. So this is the solution that I was looking for. Now let's replace the alpha back. So if you remember, we let alpha equal to this big constant, so we don't have to lug around this square root business around. So if we plug that into the equation, we can get this alpha here we have a tangent times alpha times k over m times t, and then plus that extra constant. Now, focusing on this expression, this is just a product, we can multiply inside, well, we can think about bringing this k into this square root. So it goes into the square root as a k squared. And then what that's going to do is it's going to cancel the k in the denominator, and this is gone. It's just going to be a 1. And then there's going to be a k in the numerator. So this k and this k were introduced after we brought this k into the square root as a k squared. So it went into the square root as a k squared. One of the k's canceled the denominator, and then the other k just got distributed to these two terms. And so if we just put that into one fraction, we're essentially done. We have our v of t is equal to this square root tan hyperbolic, and this is the term that they have that came from this term simplified, and then the t out there, and then we have that extra constant sitting out. So this is our final answer. And this is, except for they call this C, this is how the solution looks like in the book. And this is how we got it. All right, hope that helps.